Welcome to this explainer. Today, we're diving straight into the mechanics of how massive enterprises and city planners uncover the hidden links buried deep within their data. We're looking at a really fascinating area of machine learning known as association rule learning. Basically, it's a super powerful framework used to uncover hidden relationships and pull highly actionable connections out of data that would otherwise just be an impenetrable wall of numbers. Just picture it. Mountains of raw, unstructured noise. We're talking millions of disconnected nodes, endless shopping receipts, decades of dense medical records, or just sprawling logs of city incident reports. There is literally way too much information for any human team to scan through manually. So how do we possibly find meaningful connections in all that chaos? Well, we need a system that can algorithmically sift through millions of records, find the actual signal, and connect the dots for us. Okay, let's dive into this. Here's how we're going to break it down. We'll start with hidden patterns in big data, then define exactly what an association rule is, and walk through the rule mining process. After that, we'll look at a real-world case study on crime analysis, check out some applications in other industries, and finally, weigh the strengths, limits, and the interpretation of these rules. Starting off with Section 1, Hidden Patterns in Big Data. You know, the main issue we face with our digital infrastructure today isn't a lack of data. It's actually a lack of obvious insight. In modern datasets, the really valuable relationships are completely invisible to the human eye. We absolutely rely on machine learning to sift through that noise. But before we get into the nuts and bolts of how it does that, we need to be crystal clear about what this specific framework is and, more importantly, what it isn't. Association rule learning reveals relationships, but it does not predict class labels. If you're using classification algorithms, those are designed to categorize, like predicting if a transaction is fraudulent or legitimate. Association learning doesn't do that at all. It doesn't predict distinct categories. Instead, it just looks for attributes or events that tend to co-occur. It simply tells us what happens together. Moving right along to Section 2, what is an association rule? So, an association rule is essentially just a pattern. It takes the form of if X occurs, Y also often occurs. It describes the mathematical relationships between various attributes in your data. Think of it like retail inventory correlations. If a customer buys a high-end camera, they also often buy a specific type of lens. Or if we look at risk profiling in banking, if an account shows a sudden spike in overseas transfers, that account also often poses a higher financial risk. It's a very straightforward if-this-then-not framework. And structurally, every single rule is built on a left side, right side relationship. Over on the left, we have the antecedent. That's the if part of the equation. Like, if high vandalism occurs in an urban grid. Then, on the right side, we have the consequent, the then also often part. So in this case, then theft incidents also appear. Every single association rule you pull from a data set is going to be broken down into this precise antecedent and consequent structure. All right, Section 3, the rule mining process. So how do we actually find these things? Well, there are 4 primary stages. First, the algorithm scans through the massive dataset to find repeated combinations, attributes that show up together frequently enough to actually care about. Second, from those combinations, it forms potential rules. Third, it checks which of those rules are mathematically robust. It does this by checking metrics like support, which is how often the combination appears in the whole dataset, and confidence, how often the rule actually turns out to be true. Now, the machine does the heavy lifting for those first 3 quantitative steps. But step 4, interpreting the results, that absolutely requires a human. An analyst has to look at those mathematically strong rules and figure out if they're actually useful in the real world. Let's make this concrete. Section 4, Case Study on Crime Analysis. Imagine a police department analyzing a massive municipal database of incident reports. The algorithm churns through years of data and highlights a very distinct pattern. Areas with high rates of vandalism also often experience incidents of theft. Notice how perfectly this maps back to our rule structure. High vandalism is our antecedent, and incidents of theft is our consequent. This isn't just some intuitive guess by a detective. It is a structural pattern that emerged purely mathematically from thousands of complex police records. Uncovering the rule is great, but how does this turn raw data into operational insight? For law enforcement, it's a real game changer. It allows them to support patrol planning by routing officers to grids where vandalism is spiking, because they now mathematically know that theft might follow. It dramatically improves resource allocation.
It highlights higher risk areas before major crimes escalate, and ultimately, it powers predictive policing decisions. They aren't just reacting to crime anymore, they're using deep data patterns to actively anticipate where they're going to be needed most.
Which brings us to Section 5, Applications in Other Industries.
And look, this isn't just for law enforcement. That exact same mathematical logic is operating constantly behind the scenes across the entire global economy. In retail, it's all about optimizing store layouts and engineering those highly targeted product bundles you see online. In healthcare, researchers use it to uncover hidden, co-occurring symptoms in vast patient records, which heavily supports advanced diagnostic models. And in finance, banks deploy these algorithms to spot complex behavioral patterns that almost always happen right before a sophisticated fraud event or a default. It's the exact same if X then Y framework, just applied to completely different data environments.
Finally, Section 6, Strengths, Limits, and Interpretation.
Now, this brings us to what is easily the most critical part of understanding this entire framework. While association rules are amazingly powerful, they come with strict limitations that completely depend on human judgment. If you take away literally one thing from this explainer, let it be this. A co-occurrence is not the same as a cause. A rule is strictly about association, not causation. Just because vandalism and theft happen together in the same neighborhood, it doesn't mathematically prove that the vandalism caused the theft, or vice versa. They just happen together. Assuming causation where there's only correlation is, without a doubt, the most dangerous pitfall any data analyst can make. When you weigh it all out, the strengths are undeniable. It brilliantly uncovers hidden relations, making it completely unparalleled for initial discovery and strategic planning. It also really helps focus an analyst's attention on the most mathematically relevant areas. But you have to be extremely cautious, because like we just said, it doesn't prove causation. And crucially, it demands human interpretation. A mathematically robust rule might be incredibly actionable in one context and mean absolutely zero in another. Context is the only thing that decides if a rule actually matters. So, the absolutely crucial point here is this. Mining finds the pattern, but it's human interpretation that actually gives the pattern practical meaning. The algorithm is just a tool. It's kind of like a really fantastic, high-powered flashlight in a pitch-black room. It illuminates the environment perfectly. But the human officers, the enterprise managers, the medical diagnosticians, they are the ones who have to look at what that flashlight reveals, apply their actual real-world expertise, and decide if those clues require action. So the next time you get eerily accurate product recommendations online or read about predictive modeling in your city, you know exactly what's operating behind the curtain. It's association rule learning. But it does leave us with a pretty serious challenge as our world gets more and more data-driven. If your data could speak, would you know how to interpret its rules without jumping to conclusions? It's a question every successful data detective has to ask themselves. Thanks for joining me on this explainer.